Okay. Uh, Good evening, everyone. Welcome to week 4 problem solving session. Again, my name is Bhavya Deeprai. Okay. I am a PMR scholar from IIT Madras. Okay. And today's topic is PSPACE, Ladner's theorem, and Oracle Turing machines. Okay. And the assignment deadline for assignment 3 has just been over, so we'll discuss a few questions. This week's assignment was a bit simpler in my eyes. Okay, so only a few questions I thought were on the tougher side for this last week compared to the previous weeks, so I'll discuss those. And okay, before moving on, I'll just do a slight recap. Okay, so uh, I just want to give a, a bird's eye view of the landscape of the complexity classes. Okay, so firstly, let us look at the main problem, that is P versus NP. So I just want to draw a containment diagram. Okay, and I recommend you guys to do the same. And so you have P, and we know that P is contained in NP. Whether NP is contained in P is another question. We don't know. And another close question is with respect to co-NP. We don't know if co-NP and NP are the same thing, but we know that P is contained in both NP and co-NP, right? And next, NP and co-NP both can be generalized, okay, to be contained in the polynomial hierarchy, right? So you sigma 2, pi 2, and so on. And the polynomial hierarchy itself can be contained in P space. That is what we learned in this week. Okay. And next thing is that okay. Next, what about L and NL space? Let's look at space classes. P contains NL, and NL also contains L. We don't know whether L is equal to NL or not. One thing, what about co-NL? We know that NL is equal to co-NL. And by Savage's theorem, what do you know? We know that D space log square n contains NL, right? By Savage's theorem. And by Savage's theorem, what can we tell about P space and co-P space?
So, yeah, in fact, NL is equal to co-NL is the Immermann's.
Sorry. What am I saying? Yeah. Oh, okay. Yeah. NL is equal to co-NL is by Immermann. That is fine. But I'm saying, sorry. P space and NP space. What can we say for Savages using Savages?
Yeah, both are equal.
Both are equal, right? NP space. Now, what can we talk about co-P space?
So P space, in fact, for the space complexity classes, the original one is same as its complement.
Right. So co-P space is equal to P space, right? And we have this, and this part is due to Savages, and this part is also due to Savages. Because if you square any polynomial, you still get a polynomial, right? But that is not true for log. Okay, good then. And finally, what can we talk about EXP and AXP, exponential?
EXP, so yeah, so I think So NP would be the element of the EXP and
NP would be contained in EXP. Okay. NP is
yes.
contained in EXP. Okay. What
And I
about
can
co-NP, PH and so on?
yes. So co-NP because co-NP is if its complement is there in NP. So yes, and I so
Okay.
I'm not sure whether this co-NP is contained in exponential or not.
Sure.
Yeah,
Okay.
because if the language is can be solved in the exponential time
Okay.
with TTM, then that is in NP. And I'm not sure whether its complement can also be solved in the
Okay.
exponential
Okay.
time.
What about PSPACE? Could it be contained in EXP?
Yes. So even I think that the EXP would be the subset of the P space.
So EXP is a subset of PSPACE like this,
Yes.
and NP contains EXP. Okay. Suraj, any idea where does EXP sit in this landscape?
Set top
Top meaning
above the PP space.
above PSPACE. Okay. Why?
Um, because I think E space is contained in EXP.
PSPACE is yeah. Okay. Yeah, but why? Any idea? That is correct. EXP contains PSPACE. Okay. I'll give you a hint. Okay. Uh, can you tell me why L is contained in P?
Yes, because if the execution time, if the running, if the time complexity is say Fn, so if a Turing machine runs in the space Fn, then
Okay.
it would be requiring time of the order of 2 raised to the power Fn.
Exactly. Exactly. If it takes
So
D space Fn, then how much time? In fact, yeah. Okay. D space Fn. How much time will it? It will be
uh,
contained in D time
yes,
2 to the F of n. Right?
yes, yes. So
Here.
yeah,
Right. So if I take any function Fn, okay, D space of Fn will be contained in D time of 2 to the Fn. So if Fn is log, okay, then what do you have? D space log of n, which is nothing but L, is contained in D time 2 to the log of L, log of n. What is this? Nothing but n, which is contained in P. C log n, okay, which is equal to P, which is equal to P, right? So this is why L is contained in P. Now we are saying what is the relationship between EXP and P space? Well, just take f of n is equal to um, polynomial this time because you are taking a P space algorithm, right? So f of n equals n to the c, meaning D space n to the c is contained in D time 2 to the n to the c. This is nothing but exp contained in exp. Is it clear?
yes.
Right?
But is this relation so very strict that P space is contained in EXP?
Yeah. Okay. Let me remind you quickly about the proof why this was the case. Okay. Why can this argument be generalized? Okay. The argument, okay, that okay. Just one moment. This I think I need to. Okay. So what we are saying is that D space f of n is contained in t time 2 to the f of n. Now, why is this the case? Take any language L, okay, that takes a Turing machine M, okay, using f of n space, okay. Now, it takes f of n space, right? So, how many cells does it use? F of n, many cells it uses. These are all bits, right? And how many different types of bits can be there? Well, there can be 2 to the f of n many, right? And the proof was as follows, that you take the possible configurations that a Turing machine can be in. Okay, and a Turing machine, what does the configuration store? The head position, the tape content, right, and the state you are in. Well, this is constant. The tape content, how many ways, how many types of tape content can be there? 2 to the f of n, many types, because there are only f of n many cells, right? How many strings of length f of n, in other words. And head position log of the largest, the last cell that you can occupy, f of n. So, and these many configurations you can have. Number of configurations is log of f of n times 2 to the f of n times some constant k, which is order 2 to the f of n. So, as you can see, this does not actually depend on log. I can take any space bounded class, okay, take the Turing machine for it, and see that the number of configurations are so many. So, if there are so many configurations only that the Turing machine can enter, and furthermore, the Turing machines, the argument goes as follows, that you cannot, once you enter a configuration, after going and then you visit other configurations, you cannot come back to the same configuration. Otherwise, your Turing machine will enter a loop. So you can enter a configuration during any run, during any input computation, only once. So that means the maximum time that your machine can run would be exactly equal to the number of configurations, at most the number of configurations, okay, which is exponential on f of n. That's why you can always simulate it in this much time. That is the argument. Is that clear?
Yes, but then the Turing machine can enter into the same configuration multiple times. Is this not possible?
No, that is not possible. Well, because see, I'll tell you why. Let's say this is one configuration. Okay, the head position was at a let's say the head was at a position I. Okay, tape contains something like 0, 1, 0, and the current state is at Q1. Okay, and the head is currently reading, and then on that particular input, see, on the tape content is 0, 1, 0. Okay, right now, and then you move to another state. Okay, you move to some j, and then you change it to 0, 1, 1, and then you change it to Q2, and then you do this, and then you enter a k, and then 1, 1, 0, and then you move to a state, let's say Q1 again, and let's say you then on that particular input you entered this state back again. There's a cycle you can see, right? The state is repeating. Now what happens is you don't have any other choice. There is nothing to differentiate now, because the tape contains 0, 1, 0, and you are in state Q1 and you are in head position I. There is nothing that says you to move to another state. You are forced to move to this state, because that's how the configuration graph looks like. You are forced to move this state. Getting it?
Yes, but then I mean, what is the harm? Where is the issue if the Turing machine enters into the same configurations?
Yeah. Now, but now tell me. Now that it entered this state, it is forced to enter this state, this configuration, not the state. Sorry, configuration. And okay, then it sees a 0, 1, 1, it sees a Q2, and it sees a J. It is forced to enter this, and then it's forced to enter this, and your algorithm will never halt. Your Turing machine will never halt this way.
So Turing machine may enter into the infinite loop.
Yeah, it will get into an infinite loop.
that could be the case, and the Turing machine may run forever.
Yeah. So now that you're but then you say the language is decidable by a Turing machine M. It means that a machine is always halting. It's a decidable problem.
Oh, I see. So
Okay.
only for the decidable thing, and
Exactly. Only for a decidable problem, because you are saying that it is in D space f of n. And D space, these D space, D time P, NP, EXP, all of them are contained in decidables.
Yes, and what about the semi-decidable then? Will this statement not hold true?
No, semi-decidable is a bit vague, because see, uh, every decidable language is still semi-decidable, right?
Yes.
So if you just say semi-decidable, and I give an example of a decidable language, I give this argument, it is not enough, because semi-decidable contains decidable. Nothing is distinguishing it. But when you say undecidable, that means not decidable. Then it means that there is a loop there. Okay, the loops are allowed. If I say semi-decidable, loops can be allowed or not allowed. So, getting it?
Mm-hmm.
Okay, so since this is a decidable Turing machine, okay, halting Turing machine, if it does not halt, then there is no question about space and time.
Okay.
These concepts are only defined for halting Turing machine.
Okay, all right.
Okay.
Now I understand.
Okay, is that clear to others also, Suraj and Syed?
Yes.
Okay. So make sure that this landscape you remember well. Okay. So as the course progresses, we'll add more and more classes to it. Okay. And so, okay, a good question is like, how many of them do we know are strict subsets, strictly contained? Okay. Like, do we know that P is strictly contained in NP? No, we don't know. That's the P versus NP question. P versus co-NP is also the same thing. We don't know whether it's strictly contained. And L and NL also we don't know. Suraj says L in EXP. That is, we know that L is strictly contained in EXP. Is that correct? Yeah, that is correct. But why is it? Why is this the case that we know that L is strictly contained in EXP?
Because L is contained in P, and so therefore.
No, but we don't. We, however, do not know whether L is strictly contained in P. L versus P is another big question. We still don't know. But L is strictly contained in EXP. We know that.
Okay.
Okay. Think of a theorem.
So is this related to the time constructible theorem we discussed last time, that if it is greater than log n kind of a thing?
Yeah, time constructibility plays a role slightly, but what is the particular theorem that
hierarchy theorem, time hierarchy theorem?
Exactly. Time hierarchy theorem and space hierarchy theorem. This is why time hierarchy theorems and space hierarchy theorems are so powerful. It tells us about strict containments. Okay, so L is definitely strictly contained in P space by the space hierarchy theorem. Right, and P space is contained in EXP, so we have a separation between L and P space, therefore we have a separation between L and EXP. But same we cannot say for L and P. Okay, because we first of all don't know the separation between L and NL. So, and we cannot hope. Right now, we cannot tell anything about the separation between L and P. Okay. So, so that is one strict containment, you know. Another strict containment, can you tell? Okay, L and EXP we can separate. Can we go even finer? Can we get another separation? Can you tell me? Again, using a hierarchy theorem only. Either time hierarchy or space hierarchy.
Yes, so P and then PH, I think. P is there, and then pH starts from where? So P is equal to I think sigma 0 pi 0. What was that?
P is equal to sigma 0 pi 0. No. Remember the polynomial hierarchy, the pi sigma, we don't know a separation. We just know that they are contained with each other. We haven't obtained a separation yet.
Okay.
You mean this? No, sigma is contained in sigma 0. This is
Yeah.
strict or not, we don't know. So this entire ladder, that's why the idea of polynomial hierarchy collapsing is the question, right? If it was known that it was strict, we know that it will never collapse.
Yes.
So, yeah. Using time hierarchy theorem, we can separate P and
So this P and the P space.
PSPACE is still a space class. So,
Yes.
time hierarchy theorem talks about two different, I mean, at least directly we cannot separate them.
Yes.
So, we can separate P and EXP using time hierarchy theorem, right?
Yes.
Right? Because exp is a much larger function, and time hierarchy just says if you have a factor of log n, at least log n, you can separate them. You will always find a language which does not belong to the bigger class, the smaller class. Okay. So P and exp are definitely different. You can do much more things with exp than do with P. However, questions like whether P space is equal to P, that is an open problem. We don't know. Although P space looks like a much strong. Can we say NP is strictly contained in exp? Let me think about it. Yeah, that part I'm not sure about, Suraj. Well, you can say NP is strictly contained in any XP because of the non-deterministic time hierarchy theorem. But whether NP is strictly contained in EXP, I'm not sure about that. Because you're comparing a non-deterministic class to a deterministic class. So a direct separation, you're using a direct application of time hierarchy theorem, you cannot obtain. But yeah, I don't know. I'm not sure. Okay, maybe it is unknown. Okay. Okay. But good question. Okay, thank you. Okay, let's move on then. Said, is it fine? Oh, okay. Okay, good. Okay, so these are some questions from assignment 3. Okay, I just picked 2 questions. The other seemed simple to me, but let me know if you want me to discuss them. Okay, so assignment 3 questions. Okay, I chose just 2 of them. Okay, the first one is which of the below statements is known to be definitely true as per the correct understanding. The first question says there is a language A such that A is in P and A is not in NL. Okay, let's make solution. Let's make the diagram again. Okay, P contains NL. Okay, it is saying there is a language A such that it is in P and but it is not in NL. That is, this containment is strict. This is what it's saying. This is what A is saying. Okay. And B is saying there is a language A such that A is in P and A is not in NL. B is saying, okay, so again NP and now you have NL. NP contains P is containing NL, and this is strict. That is what it's saying. And C is saying there is a language A such that A is in NL and A is not in co-NL. C is saying NL, co-NL, and we don't know whether they contain each. Yeah, okay. We don't know whether they contain each other. And there is a language A such that A is in NL but A is not in co-NL. Something is here that is not here. And okay, our goal is saying D. Okay, let's see D. And there is a language A such that A is in, there exists A such that A is in D time 2 to the n, and A is not in co-NL. Okay, yeah, Goel. D. Why is D the answer?
So I think that just now we discussed that this L is having a strict relationship with the EXP. So L is contained in NL. I mean, it's a subset of the NL. We do not know still the exact relationship, but then NL is same as co-NL. So if L is contained in EXP, so then this NL would also be contained in EXP thing.
L is contained in EXP, that is correct, which means oh sorry, what contained in EXP, then you are saying co-NL is also contained in EXP. What did you say?
So I said that since L is contained in EXP and L is a subset of the NL.
L is subset of NL.
Yes, and NL is equal to co-NL.
And NL is equal to co-NL.
So my intuition is that since L is a subset of the NL and L is strictly contained in EXP, so therefore NL, moreover L and NL both are the subset of the P class, and P is strictly contained in EXP.
Right.
So
right.
Therefore, I think that this is true that this NL is contained in.
Right. So yeah, that's right. The final part is correct. But this part is redundant, that L is not strictly contained in EXP because co-NL is a bigger class than L. So, but the part that you are saying, it is strictly contained, P is the key. Sorry, P is strictly contained in EXP is the key. P is strictly contained in EXP. Why? By the time hierarchy theorem. P is strictly contained in EXP, and since P is strictly contained in EXP, okay, let me show you the diagram once again. See, this is the diagram. P is strictly contained in EXP means that there is a language in EXP which is not in P, and P contains co-NL, and there is a language in EXP which P does not contain, means there is a language in EXP that co-NL also does not contain, because P contains co-NL. That is what you are trying to say, right, Goel?
Yes.
Right. So yeah, that is correct. So you have EXP here, you have P here. By the time hierarchy theorem, there is a language here, let me call it L, which is not contained in P, and co-NL is sitting here. So obviously there you can use the same language L, which is not contained in EXP, but which is contained in EXP but not contained in co-NL. Good. Okay, let me write that. Okay. By the time hierarchy theorem, there exists a language L. I'll call it A. Okay, there exists a language A such that A is in P, A is not in P, but A is in EXP, So not exp exactly, this d time to the n. This is slightly different from exp. What is the difference between exp and d time 2 to the n? Can anyone tell me? Think about it. Yeah.
Can you please repeat your question? I could not hear it properly.
Yeah. Again.
Can you repeat your question? I could not hear it properly. There was some audio issue.
Right. I'm saying, what is the difference between d time 2 to the order n, which the question has, and exp? What is the difference between these two classes? There's a
Yes.
slight subtle difference, yeah?
So, I mean, I could say that, okay, in case of this EXP, this 2 could be replaced by 3 or 4 or any other number, I mean.
Well, you can raise that 2 to the log some constant and then you can still get base 2.
Yeah, but I'm not sure.
Look at the exponent instead of the base, I would say.
Yeah. So, do we have NEXP as well, non-deterministic equivalent of the EXP?
No. NEXP need not be, is not required here.
Okay, so if that is not required,
Yeah.
EXP includes its non-deterministic variant as well of the data.
No, that is not the answer. But the question I'm asking, what does it mean order n? What kind of functions can you put here?
Okay, so all those functions, I mean, which cannot go faster than the function n, right, and bounded by
Yeah,
n.
right. So can any polynomial be included in this order n?
So, yeah, not all polynomial, not all polynomial.
Give an example.
Like say n cube. So how can I write that n cube is
exactly n cube, right? So order n means it is at most some c times n, linear.
Yes.
Exp, however, is d time 2 to the order n to the c. This is the difference.
Oh, I see. Yeah.
Okay. Here the exponent is a polynomial. Here the exponent is linear. Okay. So this is the difference between these two classes. So something like 2 to the so the first one is 2 to the cn, which is like 2 to the 3n, 4n, and so on. The second one is 2 to the n cube, 2 to the n 4n. So which class is more powerful between these two, exp and d time? And by the way, this is called e. This is called e. Suraj is saying exp. Right. exp is more powerful than
e. Yes.
exp is more powerful than
yes. So, but I vaguely remember that. But there used to be a class NEXP as well, something. And
NEXP is definitely there. It's like P versus NP. It's EXP versus NEXP.
Yeah. So then the meaning of the NEXP would be that ND time and then this thing 2 raised to the power of dollar of NC.
Yeah, and that would be n time. This NEXP is this. Okay. Good.
Yes.
Okay. So that is the difference here. I just wanted to make a slide. So this is nothing but actually E, what they are asking in the question. Exactly equal to E. Okay. And yeah, okay. But I don't want to get into format. Okay. A is not in P, but A is in D time 2 to the N. And and since co-NL is contained in P, A is not contained in co-NL. So answer is D. Let's explore the other options also. There is a language A such that A is in P, A is not in NL. This cannot be true because this is the NL versus P question. We don't know. We have not resolved it yet. Okay. There is a language A such that A is that P, A is not in NL. Again, a separation between NP and NL not known. And A in NL and A is not in co-NL. A is in NL, A is not in co-NL. Then you answer, oh, how can that be? Because NL is equal to co-NL.
Yes.
Right. So you cannot have such a language. Okay. I hope that's clear. Okay. Let's look at the next question from the assignment. The question says, which of the below statements is known to be definitely false as per the correct understanding? Okay. There is a language A such that A is in P, A is not in NL. Oh, okay, it's the same set of questions. Okay, I'll let you guys think about it. It is the same options, but the question is different. Definitely false. We already gave away the answer because I already mentioned in the previous. Right. It's C. Yeah. It's C is definitely false. The others, they are open questions. Yeah, Suraj. The others are open questions, but this, we know that NL is equal to co-NL. So, C is definitely false. Clear? Okay. Okay. Great. Seth, is this fine? Just let me know if there are any doubts. Okay. Okay, I'll continue. Okay, the question says the following. Show that the following languages are in NL. Okay. So, what are the two definitions of NL? Okay. Same like NP. Let's say a language A is in NL. Then first definition is there is a non-deterministic Turing machine running in log space. Okay. Deciding or computing and deciding the language. Okay. And the second definition is the certificate definition. Okay. And what is the certificate definition for NP? There is a polynomial size certificate that and a polynomial time verifying Turing machine verifier that can verify the certificate for that particular string and then say that yes, this string belongs to the language. So the second definition is for all valid inputs, okay, for all x and a, there exists a, now this time the certificate should be read only. Certificate. I'll call it y such that and a verifier Turing machine v, okay, such that the size of y is polynomial and um, if my string were to belong to the language, if my string were to belong to the language, then my verifier machine will take the input as well as the certificate and accept. Okay, and verified Turing machine should run in logarithmic space. So I won't go into the details right now unless you ask me to, but um, you guys can ask me if there are any questions, okay, on why this is the case. Okay. So yeah. So the question says, show that the following languages are in NL. Okay. So okay, here are three languages. Can you think of why these languages are contained in NL? The first one, cycle.
Yeah, so I'm not sure of bipartite, but for the first two problems, we just need counters.
We just okay.
Like say for the cycle, they just need counters to know that whether this set of the vertices is forming a cycle. So I
Okay.
just need the information of the node numbers and basically counters. Now the only problem remaining is that for this thing I require something which uses non-determinism, because otherwise this problem can also be solved in the L class. So non-deterministically I can pick a vertex, and non-deterministically I choose another vertex. So I'm not sure, but so non-deterministically. Okay, so the meaning of NL could be that if you give me a cycle, if you give me an assignment, yeah, so then I can verify that whether that assignment of the vertices is going to form a cycle or not, and
Right.
such a verifier will run in the logarithmic space.
Right.
So therefore cycle is in NL, and similarly for the parity thing also, I mean similar logic can be used for parity. And I'm not sure, because even though you discussed in the last session that how to show that whether the given graph is bipartite or not, but I forgot it. So what was the mechanism? Except that the bipartite is too colorable thing.
Right. Right. Sure. Okay. Good. Yeah, that's correct actually. But cycle in L, that is not obvious. Okay, and because just using counters, detecting a cycle is not easy. At least I cannot think of an obvious way to do it.
No, I did not say that cycle is in L.
Okay.
So I did not say this thing. My only point is that we have been given a sequence of the vertices which is going to
no. Yeah, that was there. But at the beginning you had said of both cycle and parity being in L.
Yeah, so at the beginning I was trying to develop the logic.
Okay. Great.
Then I thought that I need to find something which requires non-determinism.
Right. Good. Okay. Yeah. So the solution, the solution you said for cycle is correct. Okay. And so how non-deterministic you can find a cycle in? Can you explain? Yeah, I'll explain that. I'm doing that right now. Okay. So so the question says that okay, you have a graph given. Okay, and you want to find a cycle non-deterministically. Okay, and using just logarithmic space. Okay, now what can log space do? Like Goel mentioned, log space is very restricted. Okay, the most you can do is count. Okay, implementing counters is how usually log space machines work. Okay, and there are n vertices. Okay, to write them in binary, okay, and the encoding will take log n bits. So how many bits can you remember in your logarithmic space, well, you are given some order log n space, which means some constant times log n space, which means you can only learn, you can remember, you're allowed to remember only a constant number of vertices. Okay, that part is clear, I think. Now, so here is an algorithm. Okay, so the algorithm is as follows. You guess, okay, non-deterministically guess length. Okay, okay, not, I won't write it in length right now, a number k, okay, which is anywhere from 0 to n or n minus 1. Okay, guess a number which is anywhere between 0 to n minus 1. Okay, now I want to form a cycle of length k. Okay, so what I do is for I in 1 to k, guess a vertex vi. Okay, guess a vertex vi, non-deterministically again. I guess a vertex vi, and I keep doing this. Okay, for 1 to k. So let's say my algorithm give k equals 3. Okay, then I'll guess a path of length 3 this way. Okay, using this algorithm. For I equals 1 to 3, I guess a vertex vi. It could be any of these vertices. Let's say I guess this one, this, and then again I guess another vertex, and again I guess a vertex. Okay, and so this forms a path, right, Suraj? This forms a path, and my goal is that I want to check if what I started with was same as what I ended with. Okay, and then that will form a cycle. So if I use 3, okay, k equals 3, then I'll guess paths of length 3, right? It may or may not form a path. That I can check looking at the adjacency matrix. But every time I make a guess, I any k equals 3 I choose, I don't have a cycle of size 3, then of course I won't get any cycle. But if I had guessed k equals 4, and I had guessed all possible paths, okay, of 4 length, this is not a cycle. And I guess this, then I guess this, then I guess this, then I guess this, then the next next vertex I guess, okay, so this should be n. Next vertex I guess, okay, is also this what I started with. Oh, then I realized, okay, I have a valid path. I mean, after every guess, I can check whether the previous, vertex is, adjacent to the next vertex or not. Then I realize, oh, I have a path. I have a cycle. Yes, I have found a cycle, and I found it non-deterministically. And even if one such cycle exists in the graph, then at least one of my guesses of the length of the cycle will be correct, and at least one of the guess of my paths will be correct. Okay, so that is the general idea. I'll make it clear here. Okay, now I'll keep this. Okay, so, and what I do is guess a vertex vi, and oops, where was I? Right. So 1 to k, guess a vertex vi non-deterministically, and check if the vertex that I just guessed compared to the previous vertex. vi, there is a path from the there is an edge from the previous one. Okay, check if it forms a valid path. In other words, check if vi minus 1 comma vi, okay, is an edge, is a directed edge. By the way, this is a directed graph here. Some kind of, okay, this is a directed graph. Okay, and check if what the sequence that I guess is actually a path. It forms a path, and then the loop will end. Okay, check if the final vertex vk is actually equal to v1. If yes, then output yes, then accept. Okay, here if it is if no, reject. Okay, so my computation tree will be something like here. Okay, and here I guessed v1. Okay, here I guessed v2. Here I guessed something else, and here I guessed v2. Here I guessed v3, and so on. And this realized row does not form a path. Then this I'll reject. And this at the end, if I reach, let's say v3, I started with guessing v1, I ended up with v3, which is not a cycle. So this is not cycle. Reject. And one such path will be there where I started with v1 or any other vertex, and I end up in the same vertex. You guessed v1 at the end, and it forms a valid path also. Okay, then I accept. And what does a non-deterministic machine do? A non-deterministic machine, okay, a non-deterministic machine will accept if even one of the computation paths are accept across all the non-deterministic choices. Even if one of the paths accept, then my machine will accept. So, Suraj, is that clear?
Yes, clear.
Yeah. Okay. So one component is missing here. So, and that is, why should this run in logarithmic space? Remember, my machine is a NL machine, non-deterministic log space machine. Why should my machine run in log space? Any idea?
Because n can be written in log n bits.
N can be written in log n bits. Okay, that is one thing. Okay, n can be written in log n bits. But let's say I'm remembering this path. Okay, and this path can be at most how long can one path be? N minus 1 length, right? Okay, how long can one path be? How long can a cycle be in the graph G? It can be n length, meaning sorry, n. It can have n vertices, right?
But sir, input we don't consider in the space complexity, adjacency matrix.
Yeah. The adjacency matrix is there. Okay, adjacency matrix is there. Okay, the input is given as an adjacency matrix. But what I'm doing is, okay, I'm guessing a path. No, how do I remember this path? I need to use my space, right? And then use so my path is v1, v2, v3, v4, v5, let's say, and so on till vn. This is the path I guessed. Right, Suraj? I guessed this path, and I store, v1 in my tape, v2 in my tape, v3 in my tape, and so on till vn in my tape. And for each of them, I take log n bits. For encoding each of them, I take log n bits. Indexing, I take log n bits. And finally, how much space am I using? N log n bits, right?
Yes.
So you can see that this is taking more than we require. This more space than we are hoping for. So why and how do we implement in log spaces? Okay, how do we implement this in log spaces? We forget the path. We don't need to remember the entire path. We just need to remember the vertex that we started with and the current vertex we are in. Let's say we are in V4. We only need to remember that we are in V4. Right? We need to remember V1. We need to remember V1. Why? Because at the end, we need to compare whether we ended up where we started with. Right? We need to remember whether what we started, the first guess of the vertex needs to match with the last guess to form a cycle. Secondly, I need to remember the current vertex, okay, or the previous vertex actually. I need to remember the previous vertex to check whether the next vertex I guess has an edge. This case, check if vi minus 1 comma vi is actually a valid edge, so that this forms a path. Okay, so need to only remember v1 and vi minus 1 at any point I and vi. Only these three vertices, remembering these three vertices are enough, because every time you're making a check whether the edge is valid or not, so you will always end up in a valid path. Okay, and v1 is required because whatever you end up with vi, the final guess, the vk you make, should match with v1. So space, how much space is required for each of them? You need log n bits. There are three vertices, so 3 log n bits. Okay, this is why this is an NL algorithm. This is a non-deterministic log space. Is that clear?
Sir,
Yeah.
so is it the case that we should also remember vi minus 2 so that we don't go back?
Yeah. Okay. Good question. So you mean something like, okay, I guessed this one, I guessed this one, I guessed this one. Okay, and this is and I have v1 here, and this is vi minus 2, vi minus 1, and vi. So we are only comparing this. You are saying we are only comparing this one. What if we go back like this?
Yes, sir.
Right. So what if we go back like this? Shouldn't we compare whether vi minus 2 is has an edge from here? But I say I don't care about that. I am fine with it. Why? Because let's say I guessed an edge from here. Oh, okay. I get what you mean here. So you mean that we don't actually end up so if you mean something like this, right? Oh, okay, yeah, okay, good. So let's say Suraj, let's say I guessed vi minus 2 once again, but I did not check, okay, whether vi minus 2 is repeated or not, but I got it again, okay, and then this went on. I get what your concern is, and this went on and went to vi. And I say that yes, there is a cycle, but this is not actually a cycle, right, Suraj? Because it's forming this infinity kind of structure. Here's an intersection. This is what you mean, no, Suraj?
Yes, sir.
Yeah. But I say yes, there is a cycle, and I get this structure. I look at, now what I do is I look at only this part. I said yes, and I get it that you are saying that this part was repeated, so this big thing is not a cycle, but it's composed of smaller cycles, right? So the fact that I'm saying yes, there is a cycle is still correct, even though it got repeated, even though the vertex got repeated. Is it clear? These smaller cycles are there. Huh?
Yes, sir, clear.
Yeah. So yeah, it's good that you raised this question. That's quite interesting actually. So if you reach here and then you repeat a vertex, you already get a cycle, and you if you still say yes, then there is always a cycle already. And if it did not reach this part, then some guess will actually guess vi minus 2 and then go this path and then reach here back again. So that part I will say yes. Okay, good. Okay. Um, okay, here, yeah, parity. Goel, what were you saying for this?
Yes, so I only said that this is similar to the cycle thing because if I give an assignment, so x is an odd number of the ones. So, but I can verify. So x is an odd number of the ones. So I'm a little doubtful now.
But yeah, but you the initial thought that you had about using a counter simply, you can use it here, right?
Yes, yes. So I require counter in the sense that uh, if you give me a number, that okay, these many ones are there in the string. So no, I'm not. Somehow I could not develop this logic. Yeah.
No, but that is correct actually. That is correct. Wait.
Okay. So if I give you the number of the ones like in decimal, say 193, there are 193 number of the ones in the string.
Yeah.
So to store this 193 number, I require the logarithmic number of the bits. So,
Right. So yeah. That would be the certificate way.
yes.
But we can do it without a certificate also, right? That's what you're saying in the beginning. Can you do it without a certificate also? Directly an L algorithm. Can we directly count one? Exactly. That's what I was saying. Yeah. We don't.
Yes.
Yeah.
Yes. You can count
Right.
once.
We don't even need the certificate. Exactly. But so you have an input x. Okay. X has odd number of ones. So what do? You have the input here. Let's say it's in the input tape, and you have the work tape, which is of log n length, order log n length. And here what you do is you initialize it to 0, 0, 0, 0. And remember, if input is of length n, so you just need log n many bits. This only need to be log n. And what do? Well, you once you see 0, 0, 0, and you actually count the number of ones. You see a 1, you add a 1 to it, and you see another 1, then you add another 1 to it, 1, 0. And you see another 1, and then you add, and so on and so forth. You keep adding, and finally you get an answer. Okay, you need to check whether it's even or not. Well, it's simple in binary. If it is even, then the last digit will be if it is even, the last digit will be in binary
0.
correct. Yeah, 0. If the last digit is 0, so here you count ones. Okay. Last digit is 0, then output no, because you need odd number of ones, and last digit is 1, then output yes. Yeah, good. Now the certificate way is how you mentioned well. So if I want to force a certificate, one certificate I can give is possible certificate I can give is the number of ones. Okay, I give the number of ones, and my verifier machine also does the same thing. First, check if this is y. Let's say y is even, is odd by looking at the last digit. Okay, y is also given in binary, and check if y is odd. Then if yes, then count once on input. So anyhow you need to count on input and then compare. So this is a valid certificate, and you just need to read only to do it. Oh, by the way, what is the certificate here for the cycle?
So yeah,
For the cycle,
so for the cycle, the certificate would be the sequence of the vertices and which is going to form a cycle, and uh, so the number of the vertices basically.
exactly. So the vertices will be the sequence which will form a cycle. Okay, and the certificate is given to you. Remember the restriction. Compare it with NP. NP is it first of all needs to run in polynomial time. Here the verify needs to run in log space. Secondly, you can read the certificate as much time as you want. Here you need to be a read only certificate. Okay, and you have the cycle. You're only allowed to read one at a time. You look at the first vertex given in the certificate, then next vertex, check if there is an edge, and then the next vertex, check if there is an edge, and so on and so forth. Only remember the first vertex in the cycle, in the certificate. That you can do it in your log space, and if you end up there, then you have verified. So you can see that the non-deterministic algorithm is actually capturing the certificate definition also, and vice versa. The certificate definition is also capturing the non-deterministic approach. That's why these two definitions are equivalent. Okay.
Yes.
Right. Okay. Okay. Good. Now the final one, bipartite. Here we need to use a property of the bipartite graph. So any idea?
So for the bipartite, except that two coloring thing, I do not remember the other criteria.
Right. But my hint would be use one of the previous either A or B.
Okay.
One of them will help you to solve this case.
So in the case of the bipartite, I think that the second criteria was that there would always be a cycle of the even length. I remember that used to be
right.
So now that we can use this one into both to show
right.
that is
Right. Verify two sets of vertices not having edges. Oh, so okay. So Suraj, your certificate is two sets of vertices that don't have any edges across them. Right?
Yes.
And okay. So let's see. Let's say something like, so the partition of the bipartite is already given to you, in other words. So you are sort of given a bipartite adjacency matrix. No, you are given an adjacency matrix, and oh, actually, this seems correct, I think. But I'm surprised that to capture the same certificate, it is not natural to. Yeah, I don't know why. To capture the same certificate, if I try to come up with a non-deterministic algorithm, it is not helping. I mean, I cannot make a non-deterministic algorithm out of this certificate. Let's see what the problem is. So I try to do this. Let's say I try to do this with a non-deterministic non-deterministic algorithm, okay, NL algorithm. What the natural way to do this would be, okay, first your certificate part gives me two partitions, right, so that there is no edge across them, and I can verify them one by one, I think. Okay, you give me some, okay, I look at the first vertex in the certificate. Okay, here is what the problem is. The problem is it not being read only. Okay, so here is the, okay, or I'll write it in a more adjacency matrix format. Okay. Okay, so the graph has a certain adjacency matrix. And now you are saying, okay, I'm giving you two partitions. Okay, and you give me here v1, v2, v3, and so on till vk, and then you are saying vk plus 1 to vn. This is the partition you say, and you claim that this is a certificate where the part A and part B do not share an edge, and I need to verify it. To do that, I locate the first vertex in v1, and then I keep going right, and I see the first vertex in v2 and compare with it, and check in the adjacency matrix whether they share an edge or not. Okay. Okay, sorry, the opposite case I need to check for is that I need to check whether among themselves they share an edge or not. If they do share an edge, then I'll output no, otherwise yes. That's what I should do, right? So I'll check with between v1 and v2 whether there is an edge or not, v1 and v3 whether there is an edge or not, and till v1 and vk whether there are edges among them or not. Right. Now I need to check whether there is an edge from v2 to v3, v2 to v4, and v4 to v, and so on. All across all pairs, I need to check here. Here there are multiple reads happening. The first time I compare between v1 and v2. Next time, and v1 and v3, and so on and so forth. I check whether this is an edge or not. v1 and v3 is an edge or not, and so on and so forth, v1 and vk, whether there's an edge or not. And then I check whether v2 and v3 there's an edge or not. But now v2 is getting read twice. This is the problem. I need to read the certificate only once. Is that clear?
Yes.
Right. But good attempt. Okay. Yeah, so let's do the certificate, the cycle way to do it. Okay. Yeah, so what are you talking,
Then
yeah?
why we are only allowed to read certificate once?
Yeah, because remember the non-deterministic log space algorithm. Okay, remember I'll give you just a what do you say, an intuitive definition. Remember the non-deterministic log space algorithm is not allowed to remember much. Okay, it's not allowed to remember much. I need to forget things as I go. I need to reuse space and so on. Okay, so if my algorithm, let's say, let's go to the cycle, let's go to the path definition. Okay, let's go to the path definition, and let's say I guess a path. Remember, I did not have enough space to remember all these people in between. I just needed, I had enough space to remember just a constant number of vertices. So I remembered just the current vertex and the first vertex and the previous vertex. Only 3 vertices I remembered. Right, Suraj? For the non-deterministic algorithm. For cycle.
Yes.
Now, what is my certificate definition doing? It's giving me the same path. If it exists, okay, if it exists, means that in my non-deterministic algorithm, the path, the computation tree will accept there. And here in the certificate definition also, I'm actually giving you the same thing. I'm giving you that path where it will accept. But here remember that now I'm cheating. Okay, I'm cheating if I allow you to read these intermediate points again and again. Getting it? Because the non-deterministic log space algorithm, we were not allowed to remember. But if I allow you to remember the certificate, then you'll be able to look back at those points and then see the other vertices also that you had previously seen. So this model where you are allowed to do lots of reads, multiple reads of the certificate. This is a more powerful model than the non-deterministic log space algorithm, right?
Yes, sir.
So this is not exactly this. This is not exactly capturing n. In fact, now I'll tell you the proper. Now that was an intuitive reason. I'll tell you the proper formal reason. This is because, okay, I'll give you as an exercise. Exercise is show that if verifier machine is allowed multiple reads, then we capture NP. If you allow multiple reads, it is as powerful as NP. Okay, so this is the formal reason for it. But the intuitive reason is that now if you give me full access to the certificate, I can misuse it to remember more information. Much more than log space. I can misuse it to remember more information. Is that clear, Suraj, now?
Yes, sir.
Okay. Yeah, Goel and Seth, is it fine?
Yes, yes.
Okay. So where were we? Okay, yeah. So here's the answer. Said, yeah. Okay, good, good. Okay. Here's the answer. Now, a graph G is bipartite if and only if it does not contain not odd, does not contain, yeah, odd cycles. And now I think you can already tell where this is going. We already know how to solve cycle using NL, remember? Okay. So G, I want to check whether G is bipartite or not. And it does not contain odd cycles. I know how to detect cycles. I can actually even tell you what the length of the cycle is. I can count and tell you the length. I can always do counting in log space. Okay. Now, and I would like you to prove this as an exercise. Okay, this part. I will not explain why, but you can see that the proof is something like, if I need an odd cycle, 1, 2, 3. If I need a cycle, I can always go from here to here, and then it will form an even cycle. This is still bipartite. But if I need to form an odd cycle, okay, if I need to form an odd cycle, I can only do it if I do this, if I misuse, if I remove the bipartiteness, because this is causing the graph to be bipartite, and I added an edge here to form an odd cycle. So it cannot be that a graph contains a bipartite graph contains odd cycles. Okay. So what I do is, okay, to check whether it is bipartite or not, I need to check whether it does not contain odd cycles. Now that is strange, right? I need to check whether something is not there. So what I'll do is I'll give you an algorithm for bipartite complement. I'll do the other way around. Since it's an if and only if, bipartite complement, G is in bipartite complement and complement both sides if it contains an even cycle. Correct? If it contains an even cycle. And this I can do it in blocks in NL. Can be done in NL. Okay. Now can you fit the rest? Now I have an now we have an NL algorithm for bipartite complement. Now can you fit the rest of the final puzzle piece? Can you give me an NL algorithm for bipartite? Checking whether it's bipartite. Yeah, go ahead.
So yeah, what is to be done, that the complement of the bipartite or what?
No, complement of bipartite is fine because it's just about checking whether there is an even cycle or not. We can use the same algorithm we used before. Now I want an NL algorithm for bipartite using this fact.
Yes, so if you give me, okay, so you give me a sequence of the vertices and along with the number, and
Right.
that gives the count of the number of the vertices in the sequence, both the things simultaneously, and yeah, that can be done. That can be verified in the logarithmic space, I think.
Or can you tell if we can use a theorem at this point instead of trying to come up with an algorithm?
Okay.
Others also try to think about it. Now I have an NL algorithm for the complement of bipartite. I want to tell there exists an algorithm for bipartite.
Yes, so okay. So in light of this statement, since I know that NL is equal to co-NL, and Immerman's fact, and since the complement of L is in NL, so if I take the complement of both the sides, so then this BIP would be the element of
Exactly. Good. Yeah.
and L is equal to co-NL. So yeah.
Right. Good. So bipartite complement is in NL. That is what we've seen. What does it mean? It means that bipartite is in co-NL by the definition of NL and co-NL. But what does this mean? Bipartite is in co-NL. This means that bipartite is in NL also. Why? Because of Immerman-Zalewski theorem, which says NL is equal to co-NL. Okay. We just showed that bipartite is in NL by showing that bipartite is in co-NL first. So this is an important strategy to actually show things are in L. There are some things that can be easier to capture using co-NL. Okay, but as you can see, we cannot use this technique in P case P to show something is in P because co-NP and P we don't know whether they are equal. Okay, is it clear? Okay, good. Suraj?
Yes, clear.
Okay, said? Okay, good. Well, this exercise, try it once. Okay, yeah. We have half an hour left. Okay, good. So, yeah, look at this question. I'll be back. Okay, look at this question. Try to answer it. I'll be back in 2 minutes. Yeah. Hi guys. Sorry, I had to charge my iPad. Yeah. So, can you think of uh, an answer for this question?
So what this super polynomial time is?
Uh, oh, okay. Sorry. Super polynomial time is anything that is worse than polynomial. Anything that is greater than polynomial. Okay. So,
Right.
super polynomial. Okay. F. Okay. Is said to be super polynomial if f is in not 2 n to the little omega of, or you can just write n to the c, little omega of n to the c. So for example, 2 to the n is super polynomial, n to the root n is super polynomial, even n to the log n is super polynomial. Okay, and so on. Anything worse than polynomial.
So can I say that a polynomial is a subset of the super polynomial?
Subset, you can always say it is less than, but subset is not a correct terminology.
Okay, okay. Because in option number 1, BFS runs in the polynomial time one thing, and since BFS would be conducting a search level by level, So I just need to again maintain a counter kind of a thing here. So therefore, this BFS may require the logarithmic amount of the space. So I think that the option number 1A is correct. However, in the option number B, the space has become the polynomial. So clearly, something which can be done in the logarithmic space can also be done in the polynomial space, and something which can be done in the polynomial time. Uh, I
Oh,
mean,
okay. I get now what you mean by a subset. Okay.
yeah,
Okay. So a polynomial time is still a super polynomial time that way.
yeah.
Okay.
So
I get now in what context you are saying.
yes. So then the option A and B both seems to be true to me.
Okay. And what about C and D?
Yes. So and regarding the Savage theorem, so Savage, we can solve path in the logarithmic space and the polynomial time. Again, this is true, but not according to the Savage's theorem as such, uh, because there is no point of using a non-deterministic thing here.
Hmm.
Non-deterministic at the so since if we can solve path in the logarithmic space, so non-deterministic machine definitely would be able to solve it in the logarithmic space. So yeah, so I think that all the options are correct in my view.
Oh, okay. Others? Okay. This is causing a confusion, so I'll remove this part. Others, anything to say? Yeah, go ahead. You have something more to add?
Nothing except this that you did not make any modification in the last option. And you did not make this super polynomial as a polynomial like.
Oh, yeah. So, okay. Yeah. Otherwise that will change the question completely. So I intentionally left the super polynomial there.
Okay.
Okay. So, okay, good. Okay, so I'll tell you. So let me shift this down. Yeah. So let's look at BFS algorithm. Okay. Can you just quickly describe how a BFS algorithm works? Like,
So it conduct search across the breadth level by
okay,
level.
right.
Yeah.
It converts search, and how does it do the? How does it remember like which path it went through and so on?
Okay. So it takes the help of a queue structure.
Q.
And, yeah, and possibly it can maintain a
Right.
set of places which have been visited or which have not been visited. So, and with the help of the queue,
Yeah.
well,
And yeah, whether it's visited or not. Yeah, said queue. That's right. So you use a queue. So at most at a time, how many people can enter the queue? I mean, out of n vertices, it may be so bad that all n, not all n, but maybe so bad that n minus one people have entered the queue, right? So I need to remember n minus one people within the queue.
yes,
So
yes,
how much space will it take? Some n minus one times log n, right? Because log n bits I'm using to remember the index of each vertex.
oh yes, yes,
So BFS will take space some n log n, which is still polynomial. It'll take
yes.
at least this much space. At least. Okay. And so this is BFS. And what about path? Sorry, what am I saying? And how much time does it take? BFS?
So probably of the order of V plus E kind of a thing.
Yeah. BFS takes, time taken is around order V plus E, and which is linear to the size of the input. No, not linear. The edges, there could be n square edges in between. So n square or something like still polynomial. time it takes is at least polynomial. Okay, good. So now between A and B, which is correct? The option B. BFS takes polynomial space, polynomial time. Okay. Now, okay, why did I post this question? You'll understand now. Savage's theorem or Savage's algorithm. Actually, I meant the algorithm for the theorem. Says BFS is breadth for search or best for search. Breadth for search. Said simply the breadth for search. Okay. The best for search uses heuristics and other knowledge, but we are only simply talking about the decision problems. Okay. So we are not given any heuristics. So simply breadth for search. Okay. So Savage's theorem algorithm. Okay, what does Savage's theorem show? Savage's theorem shows that any NL can be shown to be in the space, or actually I'll stop writing NL, I'll write path because path is NL complete. Path can be solved in D space log square n. So what does it immediately say? How much space? Oof, okay. A lot of mistakes in this question. Sorry for that. Okay.
Yes, now it makes sense. Yeah.
Right. So how much space does Savage's algorithm take?
Yes, so of order of log square.
Right. Space taken is at least log square. Some C log square. Okay. And how much time does it take?
So since the space occupied is log square of n, so time requirement would be 2 raised to the power log square of n. And if I put 2 raised to the power log square of n, then how to simplify it? So I can bring what will be the value of 2 of log square of n. So will it be 2 of log n of whole square? And
Whole of log n.
Yes. And yeah.
And to the log n.
Yes.
Right. In the worst case, I mean this is actually a loose upper bound, but in the worst case you can actually give an explicit example where if it visits all the vertices and so on. How do I shrink this? Is that not an option? Okay. You'll actually take n to the log n, and this is actually super polynomial. This is more than super polynomial. This is more than polynomials. This is super polynomial. Okay, this is what is also called quasi polynomial time. Okay, just for your information, it's called QP, quasi polynomial time. And there's another question like QP versus P and so on. But this is still more than polynomial. And so which is the answer now? The answer is now B. B and D are the correct answers.
Yes.
So right. Why I gave this question is I want you to understand the difference, in solving the problem path. Okay, I can do it in two ways. One is BFS, DFS, and so on, and one is Savage's way, Savage's algorithm. If I do BFS, it'll take a lot of space. And if I choose to do Savage's, it'll take very little space. Okay, and if I choose, and how much time will it take? It'll take less time, polynomial time. But how much time will it take? It'll take super polynomial time. Super time, super polynomial time. So you get this trade-off, right? If I use BFS, I'll use more space, but I can save time. If I use savages, okay, then I'll use very little space, but I'll blow up on time. I have this trade-off. Okay. Now, question is, and this is an open question till now, is can we obtain an algorithm for path, okay, taking log space or even log square and space is fine. Okay, because of brute force attempt, it may take more time and space. That is correct. Yeah, and space it will take a lot, but brute force is still oh, brute, yeah, by brute force you mean BFS only. So brute force is still fine in terms of time. If you see said, oh, okay, by brute force what do you mean? That comes in, but if by brute force you mean BFS only in the worst case, then it will still take some polynomial time because there are only n many nodes in the graph. But of course space will blow up. Question is, can we obtain an algorithm for a path taking log square n space or some log to the k space, okay, little space, and polynomial time? So somewhere in the middle, the perfect algorithm which will take very little space and very little time. That is what we are in search for because of brute force. Okay, in TBFS, what is TBFS? Said BFS. Okay, because of brute force, I made more time and space in PFS and DFS. Right. But remember, say even in the worst case, even if you consider it to be a brute force for BFS, the time it's still taking polynomial. But savages, it will take super polynomial time. Savages saves on the space, but you are correct that said in the worst case, in when you are considering a brute force essentially of BFS, you will take a lot of space. BFS is very bad in terms of space. Savages is very bad in terms of time. The question is, can we obtain a better algorithm which will take less space and less time simultaneously? And this is not known until now. And this is a huge problem in algorithm and complexity theory in general. Okay. Yeah. And I hope this is clear. So I just wanted you guys to know about the forefront of complexity theory right now. Okay. Is that clear? Okay, good. Okay, said Suraj.
Yes, clear.
Okay, said also is clear, right? Right? Okay, we have very little time remaining. Okay, I wanted to complete all this, but
Hi, excuse me.
yeah, said.
How can hello?
Yeah, I can hear you.
Oh, wait, you are not audible. Yeah, hello.
Yeah, okay.
How can BFS take less time?
How can BFS take less time? Okay. See, BFS works as follows, right? You explore level by level. In the worst case, okay, in the worst case, you will be exploring all the edges in the graph, all the vertices in the graph. In the worst case.
Hmm.
So you'll explore this, then you'll explore this, and then in the worst case, you will not find that node that you are looking for. In that case, you will explore all of them. So how much time will it take? It will take the maximum of the vertices, number of vertices, or the number of edges. Whichever is more, that much time you will take. Usually it's the number of edges. So and the size of the graph is the size of the graph is n, then you are only taking some order n time, right? Or order n to the c time, right? Polynomial. For us, polynomial is very small because compared to super polynomial, which is some n to the log n, it is very small. Getting it? So polynomial is actually very small time for us. Okay. In the worst case, we end up exploring all the nodes until the last node that we reach is actually the node we want, is the vertex we want. So that is when the worst case happens, and it'll still take only polynomial time. But Savages does all this complicated stuff, right? It does this halving. You check whether there's a path from v to v prime and v prime to v and so on, and then in order to save the space, we are losing out on time. We take a lot of time actually for the Savages to happen. So that's the answer. Okay.
Okay.
Okay. Okay. Good. Okay, I'll see if I can come back to this. Okay, let's look at this. Okay. Stare at this and try to answer this question. This is about reductions. Oh, okay, not even this. So this you'll be able to do. This reduction. This is more important. It's about many one reductions and Turing reductions. So if you want a reminder, I can quickly. So A reduces to B if there exists a sigma such that for all x is in A, if and only if x is in B. Okay. And A Turing reduces to B if A can be solved efficiently given oracle access to B. I hope you know. If you don't know, please let me know what oracles are. But I'm assuming in the lectures it was explained what oracle access means. Yeah, go ahead.
Yeah, so I think that since the Turing reduction is more powerful than this Karp reduction, I guess that this N is called the Karp reduction. So, so then the option number A is so if Karp reduction is there, Turing reduction will definitely be there. So option number A is correct.
Okay.
And so I think that A and B are same. I cannot differentiate in between option A and option B. I think both are same.
Oh, okay, wait. This should be T and this should be M. Sorry.
Oh, yes. So then if it is Turing reduction, then Karp reduction is not necessary. And regarding the third one, so I think that C is not true, but in the case of the Karp, if I have an oracle access to the complement of A, then I just need to reverse the output, and then I can decide the things.
Exactly.
So
Good.
I can see C is not there.
Good. Yeah, that's the answer. Okay. So. Yeah. So, see, oracle access just means that see, in a menu and reduction, you are using the subroutine directly, right? So, if it is an A, then sorry, sigma of x is in B. I apply the reduction. If B says yes, then A should definitely say no. If B says no, A should definitely say no. Now, a Turing reduction is not like that. A Turing reduction gives you much more freedom. It means if I have an oracle access to B, so an oracle is like this, a magical creature which will always give you the answer. okay, to whatever you ask for. Now B could be like a SAT problem or a path problem or a cycle, bipartite, whatever. I just ask it an answer, it'll spit out the query. I ask it the query, sorry, it'll spit out the answer. I ask it any number of questions, okay, any number of times, it will give me the answer for it. So that is what Oracle access means. Now, the first part says A reduces to B. Then it means that, there exists a sigma such that, if X is in L, if and only if sigma of X is in B. And how do I make a Turing reduction out of it? Okay, simply ask sigma X, okay, simply compute sigma X and ask query sigma X belongs to B, two oracles B. That's it. But now B is not clear. If now here if it says yes, then yes. If it says no, then no. B is not clear. If you are given Turing, if I say, okay, an oracle query, given, okay, who knows, maybe A performs many queries to B. A is continuously asking questions to B. How do I make a single question such that on being saying yes, I'll say yes, and if on B saying no, I'll say no. So that is not clear. So it is not known whether B is true or not, but A is definitely true. And again, A reduces to A complement. Many one reduces to A complement. Now this is not only not clear, this is not true at all. Actually, this is also not clear. Why? Because if this was possible, if this were true, then NP would reduce to any language in NP would reduce to L complement for L in NP. So NP equals CoNP. This would happen, but that is not the case. So this is not true. C is also not true. B is also not true yet. Okay, and A Turing reduces to A bar. Why is this true? Like Goel mentioned, A Turing reduces to A bar. Why? Because what I do is say given X as input, query whether X is in A bar or not. If X is in A bar, output no. If X is not in A bar, it is in A, that means output yes. I have a freedom to say yes or no. I can flip the answer. But why does this not work in the case that A and A bar are, when I'm taking a many one reduction? So why does the same logic not work? I said that it's not possible because NP is equal to CoNP, right? That way. But why does it not work? Because if A bar says yes, then I need to say, A also needs to say yes. If A bar says no, then I need to say no. That is the essence of many one reduction, right? So this is the right. Okay. So this is the idea of reduction. Reduction is a tool that helps us separate two classes. Okay. For a Turing reduction, NP and CoNP are nothing but the same thing. A Turing reduction cannot separate NP and CoNP. It is too strong. Okay. And I need weaker reductions to actually separate two different classes. It depends on what kind of lens am I looking. Do I need a magnifying glass or a telescope? Okay, for different purposes. If I need to separate NP and CoNP, I need a many one reduction. Okay, a Turing reduction would not be able to actually distinguish the two. It's like In the previous week, I talked about log space reductions and polynomial reductions, polynomial time reductions. Right? Why do we need these two? We need them to separate these classes, and Turing reductions is not strong enough actually to separate a language and its complement. This is the reason why. Okay. Okay, so we are already at 7:59. Anyway, I'll upload this document and please try to work out these questions. Okay. It's already 8 o'clock, so I think it's time to wrap it up. Okay, so any other questions if you have? Else we'll call it a day.
Thank you so much.
Oh, okay. Thank you. Yeah. Yeah. What did you say, Goel?
So I said that this was a very, very interesting session.
Oh, okay. Thank you. Thank you, Goel. Okay then. If there are no questions, then we can wrap it up. Okay. Everything's fine, right?
Yeah. Good night.
Okay then. Good night, Goel.
Okay, good night.
Okay. Good night, sir. Okay. Bye bye. See you next week.